So we're going to talk today about low power protocols that are employed in IoT systems. We're going to talk a bit about Bluetooth. We're going to talk about ZigBee and some other less known protocols that are used in wireless sensor networks that build IoT systems. Um, we've covered quite a few in our previous lectures. So we talked a bit about CoAP, about MQTT, about AMQP, XMPP, and so on. These are session level protocols, so to speak. What I'm interested more about today is the data link protocols themselves. So Bluetooth and Bluetooth Low Energy are very commonplace in all smartphones, tablets, and so on, and quite a few IoT devices themselves. Others might use ZigBee as an underlying protocol. LoRA, for example, is another one which is very low power and achieves quite good communications at great distance. So we're gonna briefly go through a few of these today and see what their particularities are. Now, if we can split them by range, we can actually categorize them by short range versus long range IoT. So short range IoT is anything that's basically within a home. So kind of like constitutes a local area IoT network with maybe a smart thermostat or an Amazon Alexa device or kind of like a smartwatch or a wearable that you can connect to your smartphone and other IoT devices that can connect directly to the router. So we're talking about maybe tens of meters to hundreds of meters of connectivity around your house and devices that might be plugged into the power supply or might have batteries and they might use different protocols altogether inside of a home to actually give you the whole IoT experience. Wide area IoT are devices that can communicate over a, like name says, a wide area. So we're talking about smart meters, for example, that establish a connection across a city. We're talking about hazardous events detection such as fires. We talk about smart farming. We're talking about resource and asset tracking, such as bike rental bike tracking inside of a city, for example. Now, if we categorize them by coverage versus throughput, coverage being the distance where they can actually achieve a working connection, and throughput being the bandwidth from a few kilobits per second to a few hundreds of megabits per second, then this is how you actually see these technologies. So we have on one hand Bluetooth and 802.15.4, which is the basis for ZigBee, reasonably low data rate and reasonably small distance coverage. So tens of meters to, let's say, less than 100 meters for both of these. Wi-Fi has slightly better throughput, of course, because it's tailored for, let's say, more advanced devices. So you can easily go with a throughput of more than 100 megabits per second for Wi-Fi, but the range is kind of the same as ZigBee. Um, Long range, we have a few technologies which are available. LTE comes from line telecommunication equipment and is basically the technology used by smartphones to connect to cell phone tower and actually give you your 4G or 5G internet. There are different LTE standards, and we're going to talk briefly today about LTE-A and LTE-M. These are more suited to IoT devices in a sense that the power consumption is small, so you don't need a big battery to actually achieve connectivity over a data network. LTE-M out of these two is the lower bandwidth variant, so you can actually achieve very good performance with LTE-M over long distances, and you can still conserve some battery lifetime. NB-IoT is something similar to LTE, again, spread spectrum, and then LoRa and Sigfox are unlicensed spectrum protocols, which actually give you a very good coverage, so very long range communication, kilometers up to tens of kilometers. In some special cases, you can actually have LoRa transmissions over 100 kilometers or more, and very low data rate. So we're talking about tens of kilobits per second. So you're not going to be able to even send voice or images or something like this. But it's very, very low power. So you can actually power a device through LoRa, and its battery would last for months or years. Now, whenever we talk about a low power wide area wireless network, we talk about usually low bandwidth and low power devices. These work, these two concepts work in a synergy to actually offer you connectivity and availability, even if the network has, a very wide range of coverage. So you can achieve state of the art right now, maybe tens of years of battery lifetime for your device with a very big deployment, geographical deployment. So we're talking about maybe hundreds, thousands, tens of thousands of sensing devices with very low device costs, maybe I don't know, $10 per device, but at the same time, you're not going to have a very large bandwidth. So you're going to be able to communicate with these devices maybe in a few kilobits per second. So most critical factors in such a network are, of course, the architecture, how the nodes organize, and how you actually send data through it. It can be point to point, it can be multi-hop. So you can actually have the different nodes connecting to an ad hoc network. Communication range, battery lifetime. You can also have a lot of interference in the environment, so it needs to provide some sort of robustness to that interference. You can also have maybe hundreds to thousands of tens of thousands of nodes in a network. So you gotta have a way to actually scale up the network and ensure that network capacity is met. At the same time, data that is handled through the network might come under attack. So you need actually some sort of network security protocol installed and some sort of crypting protocol to actually work with your data transmission. It might be one way, it might be bidirectional, of course, and you have a variety of applications that are served by such a network. So again, when we talk about, let's say, capability of the device itself and complexity and cost, there's this pyramid here, which actually has at its base the technologies that offer connectivity for very large number of devices, such as Bluetooth, for example, which is widespread right now in devices, ZigBee and Wi-Fi. So they offer a large volume of devices that are deployed in the field right now, and they exist and they can communicate through these protocols. But these are short-range solutions. Next level, we have LoRa, we have Sigfox and LTE-M devices, which are relatively simple, low-cost IoT solutions, which are better suited to if you want to build a low-power, wide-area network. So you want to spread it over kilometers of area or hundreds of kilometers, then these technologies work better for you. You have LTE-M as well, which is, let's say, if I have a standalone, it's built in over the existing cellular networks, and it does have some particularities and some benefits. Then, if you want to go higher in data rate, you have LTE, but that's not going to be low power anymore. And then you have, of course, 5G and so on, which can offer you very good bandwidth, but with an additional cost of draining your battery very fast. So let's talk about the main protocols that are available right now for us in IoT, and most of them are actually very low power. So we're starting with Bluetooth. Now, Bluetooth as a protocol started in 1994 to actually establish a communication protocol between cell phones at that time over very short distances. So we had an explosion in cell phones. Nokia was one of the main drivers of cell phone development back then, and it established a consortium, a special interest group, or SIG, in May 98 with Intel, IBM, Toshiba, and Ericsson. So these were the major drivers in the mobile world back then. You have two companies that actually manufacture mobile devices, so Nokia and Ericsson, and then you have Toshiba also was a manufacturer, and you have Intel and IBM, which were main players because of their silicon being used in and their software being used by these devices. So they named the protocol after a Danish king that united the Danish tribes, the Viking tribes, back in the Middle Ages. So the Bluetooth protocol was designed to unite all mobile devices or mobile cell phones back then. The first version came out in 99, and but the one that got approved and became a standard, an IEEE standard, the ITO 215.1, was back in 2002. Key features were low power. You see the current consumption figures here: 10 milliamps in standby and 50 milliamps while transmitting, which were very suitable for low power communication back then. It had to be cheap, a few dollars per device, and it had to be low footprint, so maybe a few millimeters square in surface for the chips themselves. Now, the radio band for Bluetooth, as you probably know, is in the 2.4 gigahertz range. It's segmented in different channels, but it's from 2.4 to 2.48 gigahertz. And the data rate is not necessarily great. I mean, it's from 1 megabits per second to maximum 3 megabits per second for Bluetooth. It supports point-to-point and point-to-multi-point connections. So you can have something like a point-to-point relationship between one master device and multiple slave-like devices, and then you can have also kind of like a piconet, it's called, structure, where you can have point-to-multi-point connections. So sort of peer-to-peer network, but it's very specific to Bluetooth. You can connect up to 8 devices simultaneously with this standard, with, of course, minimal interference between devices because they use a frequency hopping scheme. That's very interesting. It's you can actually hop on the channels in this this communication frequency range up to 1600 times per second. So there are 3 classes of Bluetooth transmit power. You can see them here: class 1, 2, and 3. From class 1, the highest power one, and of course, which has the largest operating range of 100 meters or more. You can have down to class 3, which is 1 meter. That's for Bluetooth standard, so to speak. Frequency hopping, kind of like a side note, was invented by an actress, Hedy Lamarr, back in I think before World War II. So it's one of those inventions that actually defined the modern world, and was done by someone which you would not really think that had their scope was set for science, an actress, but it's a really interesting side note of history, and it's really inspiring to a lot of people to actually try and do something really great. Now, for Bluetooth versions, we have Bluetooth 1.1, 1.1, which is back in 2002, and then different versions. Bluetooth 2.0, for example, appeared in 2004. Different coding schemes, so digital phase shift keying, for example, for transmission. It's low power, more low power than Bluetooth 1. Then you have Bluetooth 3, high speed in April 2009. You've got roughly 24 megabits per second when you combine the scheme with Wi-Fi. Then very important was Bluetooth 4 in 2010. It's a standard for low energy, so very small devices requiring a battery lifetime of months, even years. It's not compatible with the physical layer of the previous Bluetooth versions. So that's why it's called Bluetooth Smart or BLE, Bluetooth Low Energy. And you're probably going to see it like this. Most smartphones use Bluetooth Low Energy today, as well as Bluetooth Classic, so to speak. So the older, let's say, versions of the Bluetooth protocol are called Bluetooth Classic right now. Then Bluetooth 5 in 2016 is the latest installment, improved energy consumption and increased range for communication up to 200 meters of distance between devices. So what's with Bluetooth Low Energy? Because it's very well suited to IoT devices. So from 2001 to 2006, Nokia was doing a lot of research into Bluetooth and how to improve energy consumption with the Bluetooth transceivers. And the question they were asking was how to design a radio that can transmit short bursts of data, so not a lot of data packets, but it can do so for months or even years from a coin cell battery. So something very, very tiny, very low power. The answer they found was to keep the radio asleep most of the time. So you will actually duty cycle a lot the radio chip to actually achieve these very long battery lifetimes. You can actually achieve advertising on only one of 3 channels. So Bluetooth Low Energy has a restricted range of channels, and you can transmit data quickly at a restricted data rate, so a maximum of 1 megabit per second. And minimum time to send data is only 3 milliseconds. So you can imagine you're not going to be able to squeeze a lot of data packets into that window. Maximum transmit power is limited to 10 milliwatts, so it's not very long range. Of course, it's only going to be able to connect over, let's say, 10 meters of distance, or maybe 20 meters maximum between the receiver and the emitter. So it's doing this, but it's also achieving some sort of security. It's coded through AES 128-bit code. So what trade-offs were made here? Well, the protocol is designed for transmitting tiny packets of data. So you're not going to be able to transmit large image files, for example. You're not going to be able to transmit real-time voice. You're not going to be able to transmit video. You're only going to be able to transmit packets, very small packets of data, such as readings from some sensors, maybe data packets from your wearable device, your wearable band or smartwatch, consisting of I know, biometric data or accelerometer steps, calories, and so on, which are packetized and do not consume a lot of bandwidth. A maximum is per packet is of 20 bytes. So you cannot send more than 20 bytes in a packet. And you have 4 main operations: read, write, notify, and indicate. This is how the Bluetooth communication over Bluetooth Low Energy communication is actually done over time. So you can see periodically the device wakes up and advertises its presence, and then whenever you have a connection, you see these bursts of data, so radio connectivity, and then you see also periods where you have total silence on the radio channel. So it's you're not continuously transmitting over the channel, rather you're transmitting in bursts and then going to sleep and then transmitting in bursts again, and so on. So it's a scheme where you duty cycle a lot, the radio transmitter, in order to obtain very good current consumption. So the naming for Bluetooth 4.x is officially Bluetooth Smart or Bluetooth Smart Ready, This is the SIG preferred name, but most people and most companies use Bluetooth Low Energy as the name. So you're gonna find probably both notions in documentation, but most likely you're probably gonna find BLE or Bluetooth Low Energy with your devices. So it's, let's say, 1% to 50% of the power consumption of Bluetooth Classic. It's like I said, enabled for short broadcasts. You can send your body temperature, heart rate. It's very good for devices that do not send a lot of data, automotive or industrial devices, and so on. If you want to do voice or video file transfers, it's going to be very complicated, and it's not going to be real time. So even if you want to send a file of, I don't know, maybe a few megabytes, you're going to have to wait quite a long time, maybe a few minutes for it to fully transfer. Small messages usually. So you have a throughput of around 1 megabit per second, but it's not necessarily critical, so it's not necessarily guaranteed. Battery lifetime, because of this, it can be measured in years, depending, of course, on how often you communicate through the network. So if you communicate maybe once every few hours, then this is easily achievable. If you communicate maybe every minute, then you're probably not going to be able to extend the lifetime to a year, but you're probably going to be able to extend it to a few weeks, for example, which is something that regular smartwatches and smart trackers they offer today. Most, if not all, of the wearable devices right now use BLE as a standard, so they connect to the smartphone using BLE. The topology of the network is very simple. So you have most of the connectivity is star topology. So you have maybe peer-to-peer connection between, I don't know, your smartwatch and your smartphone. There are no scaternets, no meshes, and so on in Bluetooth 4.0 at least. It's low cost. It's costing less than a Bluetooth Classic transceiver. So you can actually, it's an incentive actually to build a lot more devices, Bluetooth Low Energy devices, than Bluetooth Classic devices. And it's designed on an earlier protocol designed by Nokia. It's called what's called Ieee. All new smartphones, be it iPhones, Androids, and so on, have BLE also as a standard. So as a Bluetooth transceiver, you have a dual mode functionality where you offer Bluetooth Classic and you also offer Bluetooth Low Energy. Now, there are 4 main BLE roles for a device. You can have a central, which is actually kind of like a gateway or a server that the devices connect to, or a master, or so on, depending on how what terminology you find. You have a peripheral, which is kind of like a slave device or an end node that can also read, write data, and can send data to the central device. You can have a broadcaster, so kind of like a repeater where you have read-only broadcast data that you want sent in the network. And you have an observer role that can receive broadcast data. So depending on the state, each of these devices can act in a certain way. So the central, for example, can act as an observer, can act as a broadcaster as well, depending on how you actually configured the Bluetooth chip. So the topology is very simple. Bluetooth 4.0 standard specifies a Piconet architecture in which you have point-to-point connections between it's called a master unit and slave unit. You can have multiple slave units connected to a single master device. You can see this master device as I don't know, as a smartphone, as a tablet, and then different IoT devices connected simultaneously to it. Then Bluetooth 4.1 has this this specification of a scatternet. So it's kind of like multi-hop network that you can establish across multiple master and slave devices. in a network. So you can have data sent over over this network in a multi-hop fashion. There are 5 power states for a BLE device. So you can have, let's say, a scanning device, which is not actively connected to anything, but it's periodically waking up and beaconing its presence. So you can actually connect to it. Then you can, when there's a connection, whenever there's a connection event, or you want to advertise your presence, you actually jump to a standby state where you can actually advertise. If there is a peer nearby, you can actually connect, so you can jump to a connected state. Or you can actually, from a standby state, you can jump to an initiating state where you actually prepare a connection. So these are the main power status states in a Bluetooth low energy transceiver. Now, in terms of the communication channels, you have them spread. So there are only 3 communication channels taken from the Bluetooth Classic specification. You have channel 37, 38, and 39, which are reserved for advertising, and then other 37 channels reserved for data. So whenever you have a device which is actually looking for a connection, you use these channels to advertise, and then you can use whichever channel you like from the 2.4 gigahertz range to actually connect. You have a maximum connectivity range of 150 meters, depending on the power you actually configure the physical chip to emit. So you can have a maximum of 10 milliwatts of power, which in an open field will give you a few, tens of meters to up to 150 meters. These advertising channels, these 3 advertising channels, were selected to avoid especially the interference with Wi-Fi channels, because it's Wi-Fi, it's overlapping the 2.4 gigahertz range. So you're probably going to have a lot of interference with some of the channels here. Okay, the MAC itself for Bluetooth Low Energy specifies 2 device types: a peripheral and a central. The peripherals are simpler than a central device. So even let's say low power, low cost, more low cost than the central device. And there are let's say different states, 4 actually different states. Non-connectable advertising: you broadcast data in clear, and everyone can actually listen to that broadcast data. You have discoverable advertising. The central may request more information pending a connection, and the peripheral can send data without actually establishing a connection to the central. General advertising, the broadcast presence wanting to connect. Central may request a short connection in the state, and then directed advertising, it's a connection state where you transmit signed data to a previously connected master. So this is basically how it works, and this is how you actually can send these advertising packets through any of the 3 channels for advertising, 37, 38, or 39, and then you can actually scan connectivity on these channels. This is how the communication is done between a peripheral and central before actually establishing a connection. So this is the handshake that can be done before getting a connection request from the central. If you have any questions, or you'd like to know more, please let me know. Okay, moving on. Now, very interesting is the Bluetooth Smart Protocol stack. So these are the layers of the Bluetooth general protocol stack, from the physical layer, link layer, host controller interface, logical link control, different attribute protocols and security managers. And then you have the generic attribute profile, or GAT. Generic attribute profile is a very important data structure, actually, which is used by Bluetooth to communicate different attributes between the host and the controller. So you can actually specify, you have it built in for Bluetooth and Bluetooth Low Energy as well, the type of device and the role of the device that it's connecting to. So you can send a lot of information which is related to, let's say, the application itself. It's got this built-in profile which can be used to target a specific application. What I mean by this, so the GAT itself, it encompasses a profile which can have multiple services, and each service can have multiple characteristics. Now, what is the characteristics? Characteristic is it's a descriptor which it's actually a data structure. It has values and different descriptors. So you can attach different descriptors which are called attributes. They are identified by unique unique identifiable IDs. So, for example, these can be of 16 bits of length or even 128 bits of length. So you can have very unique identifiers for different, let's say, parameters. For example, you can have a service called heart rate service, which is targeted to devices that measure the heart rate, and you can uniquely identify a heart rate device through its characteristics. So you can have a characteristic which is targeted exactly for heart rate measurement, and then another characteristic within that service for body sensor location, so where the sensor is located on the body. So, for example, on the torso. So it's got built-in specifiers that actually help define the application. The central can actually do operations to discover all these unique identifiers for all primary devices and find a service with a given unique identifier. So you can actually interrogate and you can actually go through the list of identifiers and find that which is interesting you. So you can connect to a device and get only the heart rate or the pulse or whatever. You can have secondary services for a given primary service, which is specified by this, and you can discover all these characteristics for a given service. You can match the universal unique identifier here with a given one, and you can actually browse descriptors, read them, of course, write, and so on. So you can do all sorts of operations. A peripheral can only notify or indicate central if anything changes. So you can actually do that. Now, on the security side, I told you it's an encryption scheme of 128 bits over AES. It's got pairing, so you can actually have a shared key pairing type of connectivity. You had a bit of a loophole in Bluetooth 4.0 and Bluetooth 4.1, which was passive eavesdropping. During key exchange, you could have eavesdropped the communication and deducted some of the communication protocols out of it, but it got fixed in Bluetooth 4.2. So there's, let's say, enough security for this, but for some applications or other companies that manufacture Bluetooth Low Energy device, they choose to also build their own security on top of what BLE is offering. So you might have another security protocol on top of this encryption scheme here. Now, what are the applications? Well, you can have proximity applications. So, for example, in a car, in a certain hotel room, or I don't know, maybe in a shopping mall, you can have different locator applications, such as locating your keys, locating your watch or your phone, locating your pet, and so on. You can have health devices. all sorts of heart rate monitors, physical activity trackers, smart thermometers, and so on. You can have different sensors, which are smart, I don't know, smart thermostats, for example. Tire pressure also can be measured by this. You know, you have smart sensors which are embedded in your car tires, and you can have remote control, opening, closing locks, turning on lights, and so on. So these are some of the main applications which are particular to Bluetooth Low Energy. So you have something like physical security. You can open remotely your hotel door just by being in proximity to your smartphone. You can have a home automation app which can connect to different IoT devices in your home, and different key fobs that you can attach to different things, and you can locate them, or you can have different smart buttons, such as Amazon smart buttons. You can order different items just by pushing the button. You can have interesting applications of geofencing or positioning within a shopping mall, or within a supermarket. You can actually find your way, and you can find different products which are on sale. You have all sorts of fun gadgets and toys which use Bluetooth Low Energy, so mini drones and cars, things like these. And you have a lot of development kits and boards available. The SP32 as a kit has Bluetooth Low Energy, and we're gonna, in the lab today, we're gonna go over an example of connectivity between the board and the smartphone over Bluetooth Low Energy. Now, this was all about Bluetooth. Let's talk a bit more about other protocols. ZigBee is one of them. It's a technology standard created for the control of sensor networks. It's suited for, again, very low cost, low power wireless devices. It's even more low power in some instances than Bluetooth and Bluetooth Low Energy. At its core, it has this 802.15.4 standard, and which was created by a ZigBee alliance. So just like the special interest group for Bluetooth, so Bluetooth SIG, an alliance of companies was created to actually specify the standard. From this alliance, you have Philips, Motorola, HP, Intel, and so on. It was conceived in '98. It was standardized in 2003 and revised in 2006 as a standard. And while Bluetooth was focused mostly on cell phones and smartphones, and IoT applications came afterwards, ZigBee was conceived for IoT applications, period. So it was conceived to cover different smart devices, smart meters, and so on, which can connect in a multi-hop network. So it has multi-hop built in, not unlike Bluetooth, which was kind of like started as a peer-to-peer connection. It gradually grew into smart, sort of like a mesh structure, but not a fully connected mesh, such as ZigBee. It's got very good coverage, so it's very robust radio link, very resistant and tolerant to interference. You can have mesh networking, so you can have multiple connections to devices, and you can have multi-hop connections. You can have the devices establish an ad hoc network. It's very tolerant to interference, even though it uses the same frequency range as Wi-Fi and Bluetooth. It's much more resilient in terms of in terms of connectivity. So whenever you have a very crowded radio environment, such as maybe at a big electronics fair, CES, where you have a lot of radio transmitters, all of them trying to connect, Bluetooth, Wi-Fi would fail, but ZigBee would still work. So it's also proven coexistence. You can have multiple radio products, multiple radio deployments working side by side. And it's very scalable, so you can have tens of thousands of such devices working together in a network. Now, basic network characteristics are here. You can have maybe tens of thousands of client nodes, 65,536 to be more exact. I think it's a 16-bit address for each of them. You have 27 channels over 2 bands of frequency and a maximum of 250 kilobits per second data rate. So it's slightly lower than what Bluetooth can offer. And it shows that its intended purpose is mostly IoT devices, which have a very low data rate. So it's optimized for timing critical applications, power management application, and it's got a full mesh support. You have these nodes which each have different roles within the network, and it's very low power actually. So whenever we look at the bit error rate versus the signal to noise ratio for Bluetooth, Wi-Fi, and ZigBee, you can see that going this direction into the graph, you have more robust communication, and ZigBee offers by far the better choice. So you have a better signal to noise ratio and a way better bit error rate than the other communication protocols available. I told you there are different frequency bands. So for a worldwide frequency band, you use the 2.4 gigahertz bands. So from 2.405 to 2.480. There are 2 different bands of communication in Europe and in Americas for less than 2.4 gigahertz, so in the hundreds of megahertz range. You have 8680 megahertz in Europe, and then you have the 900, 928 band in the Americas. Now, the architecture for ZigBee is, let's say, also similarly to Bluetooth, targeted towards applications. So you have a lot of thought and a lot of work put into how devices initiate and join the network, how you can manage the network, how you can determine device relationships and send and receive messages. So this is all handled at the application level. You also have some security functions, so you can have a security built into the network. And of course, you have different device roles. So there are 3 main device types in ZigBee. You have a coordinator. It's the node required for each ZigBee network. You cannot have a network without having at least one ZigBee coordinator, and it initiates the network formation itself. You have routers within that network. A router usually participates in multi-hop routing for messages, so it can act as a repeater of signals passing through the network. And then you have an end device or an ED. This is the end node itself. It does not allow associating your routing, so you can only connect to it through a router, and it enables very low-cost solutions. So these are the simple topologies that can be achieved through a ZigBee network. So you can have a simple start topology, for example, where each node, be it an end device or router, connects directly to the ZigBee coordinator. You can have a mesh structure where you have the coordinator and then through multiple routers, one or many routers, you can actually reach the end devices, and data can connect, can actually be sent through this multi-hop pattern from and to the end device. And then you can have a cluster tree topology where you have, again, the coordinator as a central role, and then you have one or multiple routers, and then you have maybe a single hop or a multi-hop to the end device itself. So at any rate, you need to have at least one ZigBee coordinator in such networks. Now, as I told you, it's also it's very targeted towards applications, so much that it has public profiles, something that it enables you to actually tailor your ZigBee network towards a specific type of application. So these are the, let's say, 6 public profiles that are included in the ZigBee specification: home automation, smart energy, commercial building automation, healthcare, telecom, and remote control. There are, of course, other profiles which are proposed by member companies, and they can be included within the standard, depending on the application type. Now, for home automation, for example, you can actually achieve some sort of home control. So you establish a ZigBee home area network where you connect different appliances, heating, security, lighting, window blinds, and so on to this the central node, central ZigBee node. You can also integrate smart energy and home automation. So you can add to your home automation network also the utilities on smart meters and so on that you can actually get data from your to your gas company or your energy supplier company and so on. Now moving on, the third protocol we're going to talk about today is WirelessHART. Now, HART stands for Highway Addressable Remote Transducer Protocol. It's a industrial protocol, communication and data protocol designed to add additional information, not only diagnostic information, but also data information to devices which are compatible with the legacy 420 milliamp analog current loop instrumentation. So you have these sensors, these industrial sensors, and by standard, they can send information in an analog fashion over a 420 milliamp current loop. So, for example, you can have a pressure transducer which can actually send data over this current loop, and you can encode maybe a pressure within this range of 4 to 20 milliamps. And over that current loop, it can also modulate information through this HART protocol. So you can have a dual scheme where you send analog data, and together with the analog data, you also send digital packets to a PLC or another sort of automation device. So the overall performance has been designed to satisfy process automation needs. So it's very targeted towards industrial applications, and it's able to work on slightly larger distances than Bluetooth and ZigBee. So we're talking about 1500 meters for WirelessHART. WirelessHART is an extension of HART. So HART is wired, so it's wired over that 420 milliamp current loop, while WirelessHART is designed to be, like the name says, wireless over a radio transmission. So just as ZigBee, you can implement mesh networks through WirelessHART. You can have all sorts of publish subscribe messaging, and it has some particularities which we're gonna talk about in the next slides. Now, as an overview, WirelessHART targets sensors and actuators usually. So you have these field devices which can be different industrial sensors. So you can have flow, pressure sensors, position sensors, and so on. That are used in all sorts of industrial automation scenarios. And then you have actuators. The actuators can be relays, the actuator can be motors or some sort of linear actuators and so on. So you have a very targeted focus towards industrial automation application in this. As main characteristics, you have low power consumption and very low cost devices, exactly like Bluetooth and ZigBee. The data rate is very similar to ZigBee, so you have 250 kilobits per second over the 2.4 gigahertz range. You have 15 channels of communication in that frequency spectrum. It's based on 802.15.4, just as ZigBee. But the data link layer is proprietary. So it's got a TDMA and CSMA collision avoidance scheme. It's supporting channel hopping and channel blacklisting, and you have an application layer which is fully compatible with the wired level of HART. Now, this is a comparison between HART, WirelessHART, and ZigBee, given the similarities between WirelessHART and ZigBee. What's interesting here is, of course, you use the same standard as the physical layer. The data link layer is different. So you have a time synchronized channel hopping scheme for WirelessHART. For wired HART, you have a token passing scheme of, let's say, a master device and one or multiple slave devices which are connected in that current loop configuration. Now at the network layer, you have a mesh network, both for WirelessHART and for ZigBee, but there are differences in how that mesh network is established. And again, it's a proprietary stack for WirelessHART here. Now, as a network architecture for WirelessHART, you have four main elements. You have field devices, which include WirelessHART process transmitters, wireless adapters, and so on. You have gateways. So you can have a device which acts as a gateway bridge through the WirelessHART network to a wired infrastructure. You have a network manager, and this is only one in such a network. Similar to a ZigBee network, it is responsible for network configuration, communication, and management of the messages in the network. And you have a security manager. This is an interesting particularity of the WirelessHART network, which deals with security and encryption. It sets up session keys and periodically changes the session keys for communication in the network. You might have also different devices which are used for maintaining purposes. You can debug the network through them. They can be handheld, but these are optional. A network consists of devices which are these four types of devices. So this is a typical network architecture. Here you have these field devices which are connected through a WirelessHART network. You have this access point or gateway which connects to let's say the HART network, where you have a network manager and a security manager. And then through the gateway, you connect to a wired network. It can be the plant or the industrial network that is installed inside of the factory. And you have different host applications which can actually connect to the whole network. Okay, Z-Wave is another protocol. It's a low-power MAC protocol. It's designed for home automation and has been used in IoT communication. It covers roughly a 30-meter area, point-to-point communication. It's suitable for small messages in IoT applications. Again, light control, energy control, wearables, things like this. So you don't have a lot of bandwidth available. It uses CSMA, CA as a collision detection and connection scheme. And it has a master-slave architecture, very similar to what's happening in Bluetooth and ZigBee. The master device controls the slave devices. It sends the commands and handling scheduling of the whole network. It's very similar with ZigBee with a few differences. So both Z-Wave and ZigBee are mesh networks. So they can establish mesh networks and have nodes act both as wireless data sources and repeaters. Both technologies use 802.15.4 as the main protocol for low rate data networks, but it's got different medium access control schemes. And both are widely used in local area networks and data networks. Recently, ZigBee has gained more traction than Z-Wave as a whole. Difference is Z-Wave has a tightly controlled product ecosystem. So This is let's say more regulated, whereas ZigBee can be used for a large number of applications. So there's no expectation, for example, that two ZigBee devices are interoperable unless this is pre-planned. On the other hand, for Z-Wave, it will almost always integrate with another Z-Wave device. So you have two Z-Wave devices, they can always connect. Two ZigBee devices, well, they can most of the time connect, but it's not a guarantee. ZigBee uses this 2.4 gigahertz frequency band, whereas Z-Wave uses the lower data rate 915 band in the US and the 868 megahertz RFID band in Europe. The 2.4 gigahertz band can be subject to interference, so this is why it's not preferred by the Z-Wave devices. At the same time, it's lower data rate, so you cannot send as much information through an 868 megahertz band here in Europe, but that's not necessary for most Z-Wave applications. Z-Wave uses a proprietary radio system design, so there is only one company that actually manufactures these designs, whereas there are multiple providers for ZigBee radios. And as a communication method for modulation, Z-Wave uses FSK, so frequency shift key modulation, where ZigBee is, modulation for ZigBee is through direct sequence spread spectrum, so DSSS. Another interesting protocol is IEEE 802.11ah standard, which is also called Wi-Fi high-low. It's spelled like this, HA low, but it's called Wi-Fi high-low. It's a standard which defines communication through 802.11 wireless networks. So it might be compatible to some routers or switches that actually employ this standard. But it uses sub-gigahertz frequency spectrum to actually communicate. So you can only connect 900 megahertz or 866 megahertz in Europe devices to this standard. It's targeted to IoT devices which have a low bandwidth and low data rate, and Bluetooth, ZigBee, Z-Wave, WirelessHART, and so on, they're not compatible to Wi-Fi infrastructure. Whereas this standard can be compatible, so you can connect directly your IoT device to a wireless router. So it takes out gateways or other ways of routers and so on, which can actually interface through a network. It decomplicates everything. It makes everything simpler. So you can have point-to-point connectivity between devices directly to your Wi-Fi router installed in your home. So it's got as a scope, it defines this physical layer operating in licensing set bands below 1 gigahertz, so 868 in Europe and 900 megahertz in the States. It's optimized for range and low data rate. So you have a transmission range of up to 1 kilometer in this frequency band, and the data rate is around a few hundreds of kilobits per second. And most importantly, because it's tailored to IoT, the MAC itself is designed to support thousands of these connected devices. So you have different use cases for 802.11ah or high-low. You have sensors and meters, for example, which are connected to or in the vicinity of a home. You can have sensor and meter data in backhaul aggregation, and also you can have an extension of the range of your Wi-Fi for outdoor applications, for cellular traffic offloading and so on. So you have a big enough data rate in this frequency spectrum to actually send real-time voice over the network. There are a few advantages, of course, of transmitting in sub-gigahertz frequency range. You have very good propagation and penetration of the signal. You have a relatively larger coverage area than 2.4 gigahertz, and you can actually have a larger connectivity through, let's say, maybe a few hundreds of meters or up to 1 kilometer. You don't need a license or a very light licensing scheme depending on the power of your transceiver, and it's very reliable. It's a less congesting frequency band. 2.4 gigahertz is very congested, whereas 868 or 900 megahertz is comparatively less crowded. And of course, it gives you better battery operation times. So you have a longer battery lifetime for these transceivers. You have different channels, of course, within this range. So you have a configurable bandwidth of 4 channels of 16 megahertz each. And these are inherited from 802.11.AC. It's different modulation schemes. These are let's say, this is the pyramid of throughput and coverage from different, different frequency ranges of the channel and the data rate. So, of course, a larger channel implies a better data rate. Shorter channel of communication, smaller data rate for communication. The Mac, there's a need to reduce overhead. So at low data rates and short frames, you can have short MAC headers and beacons, and you have an implicit acknowledgement. You don't need an ACK, and the need to support thousands of associated devices to increase coverage. So you have thousands of these devices, and there's a huge collision probability. Then you have a way to actually modulate this, into a restricted access window scheme. This is a diagram of how you can establish a multi-hop relay operation over Wi-Fi halo. You can extend your access point coverage, and you can have a scheme where you can have different relays. So sort of like routers, which can act as relay to these leaf nodes. Now, in summary, it offers long range, it offers scalability, so a lot of nodes, and it offers better efficiency than regular Wi-Fi connected schemes. LTE, it's another protocol. Line telecommunication equipment advanced, or long-term evolution advanced, LTEA, set of standards designed for end-to-end communication and IoT applications in cellular network. So these are over the existing cellular interface and infrastructure. It's scalable, it's low cost. It uses special modulation scheme, OFDMA, and it's a special MAC layer access technology, dividing the frequency into multiple bands. Each one can be used separately for communication. There is the architecture, which is actually drawn up here. You have a core network, and radio access network, and mobile nodes which connect to it. The core network is responsible for controlling the mobile devices, keeping track of their IPs within the network, and the radio access network is responsible for establishing control and handling of the data wireless connectivity. LoRa is I think the last protocol we're going to talk about today. LoRaWAN is a wireless technology. It's designed for low power, wide area network, low cost, mobility, security, bidirectional communication. It's optimized for scalable wireless networks, which can have millions of devices connected to them. You have redundant operations. You're not set on a certain location. It's very low cost and designed to be very low power. It can even employ energy harvesting to power itself. So this is kind of like the LoRaWAN stack of different protocols, and you have the system architecture for the network. The LoRa physical layer enables the long-range communication link itself. So again, it's targeted towards establishing connectivity at very low power, low bandwidth rates, but with very long distances between the communicating nodes. And it targets IoT applications in general. So originally it was developed by a French company, Cycleo. It was founded in 2009. It's patented as a spread spectrum wireless technology. It was acquired by another company called Semtech in 2012. And then Semtech released their first LoRa chip, this one. It was at that time using a frequency shifting modulation scheme specific for smart metering devices. So the transmission distance for LoRa was at around a few kilometers. So you can easily connect a smart meter directly to the office of the utility service or the utility company within the city. So you don't need to actually go periodically and check your meters. They can connect directly to the utility company. So there are two major components in a LoRa network. You have an end device or an ED, and you have a base station. These end devices can be anything. They can be attached to metering solutions. They can be attached to pets. They can be attached to different alarms and sensors within a home and so on. And you have the base station, which aggregates the communication. Of course, you can have base station act as a gateway to a more standard network like the 3G, 4G, and so on, or the wired Ethernet network. You can connect directly to the internet. As a network protocol, is optimized specifically for energy limited end devices. So it's designed for devices that can be operated by batteries, and it's designed to last for years. But of course, it's not designed for very high bandwidth of communication. Usually, it establishes a star topology. So these end devices, they communicate to the base station nodes, and they relay data messages to a base station node, which can connect to a server. So basically, this is the architecture. You have the end devices, which can connect to the base station, which is a LoRa concentrator here, which can act as a gateway through Ethernet or another network to a different server where you can connect to and see your relevant data. Now, regarding network capacity, you have an adaptive data rate. What does that mean? Well, whenever you have a lot of devices, for example, which are connected to a LoRa base station or a LoRa concentrator, you can have, let's say, a high data rate over a shorter range. So you can imagine having an IoT application within your home, and you have these devices which are connected over tens or hundreds of meters. These can connect and have a higher data rate to the LoRa concentrator. You can actually build what is called a local microcell under this LoRa concentrator, but at the same time, you can connect to a more remote LoRa concentrator. You can have maybe thinner spread network of devices which have a longer range of communication. And as the range of the communication increases, then you have a lower data rate scheme. So you cannot connect over a long range and use a high data rate modulation. So what it does actually is try to scale the network size, and depending on the communication distance, you actually achieve the same battery results, but with higher or lower data rates. So this is, for example, an example of how you can actually have all the sensors in that microcell connect to a remote concentrator, but for a lower bandwidth connection. There are three classes of end devices for LoRa. A are battery powered sensors, very energy efficient, so very long battery lifetime, but lower data rate. So a lot of communication latency for them, or longer communication latency. B would be battery powered actuators. These are a good trade-off between lifetime and communication latency. And C are main powered actuators. These are devices that are not battery powered, so they are mains powered and they can afford to listen continuously. There is virtually very low or no latency for communication with them. This is a table of different data rate settings and frame characteristics for LoRa. So depending on the data rate setting, you see it's an integer from 0 to 7. So you have 8 data rate settings in total. You have different frame characteristics and basically different throughputs for your communication. In this table here, you have the maximum throughput per LoRaWAN connected end device. So again, you can see the maximum throughput added through each channel in bits per second. So you have from 0 data rate, it's very low, 146 bits per second, to the number 7 data rate, which is 45K roughly kilobits per second. And of course, this is at 100% duty cycle. When you actually duty cycle the transceiver to maybe a 10% duty cycle and 0, 1% duty cycle, these numbers scale. So of course, this is 10 times less, this is 100 times less, and this is 1,000 times less. But even so, you can achieve good data rates, and you can extend the battery lifetime of the device to months or even years. Now, if you put them all together, comparing LoRa with LTE Cat M and LTE Cat 1, these are the main characteristics. So you have different modulation schemes, of course. The bandwidths are widely different. So you have a few kilohertz of bandwidth here, whereas in Cat M you have megahertz of bandwidth. Data rates are also very different, from bits per second in LoRa to a maximum of 50 kilobits per second. You have megabits per second. You might have megabits per second in LTE communication. Maximum power is at the same time comparable. So as a conclusion, LoRa as a technology it's got its pros and cons. So it has some strengths, it has some weaknesses. The strength of LoRa is the very high coverage, scalability is very good. Drawbacks are very low reliability and potentially poor performance in terms of downlink traffic. So whenever you have a communication channel open over a very long range, then it can suffer in real-time aspects. So you can have a very large latency of communication. Okay, any questions so far? This is the end of the lecture for today.
For me, no, it was pretty clear.
Okay, good. So these are the main protocols that we might be using for an IoT application. And I tried to summarize the main protocols depending on the range. So from short range communications, Bluetooth, ZigBee, Z-Wave, to medium, 802.11ah, to very high range, so LoRa, for example. There are others, of course, which we haven't actually discussed here, but they are particular to some sort of application, and they're maybe not so well known as these. Okay, if there are no other questions, thanks. Let's